So good morning, everyone. So today our topic is fluid statics. And some of the things we need to know. The term relative density and specific gravity is very commonly used in fluid statics. And you should be very comfortable with these two things. Those terms, relative density and specific gravity, both are ratio of density and both are dimensionless quantity. And if we know the density of any material, if we know the relative density, we can find its density. Because if relative density is, say, like for mercury is 13.6, it means if relative density is 13.6 times more dense compared to water, and its density will be 13,600, which is 13.6 times density of water. So how to calculate density of mix, we discussed last time, that we should be thorough with. And important point I'm just touching on again is pressure. So liquid pressure is a little different from kind of pressure exerted by solid. See, we stand on ground or you keep an object on a surface. Any object which has weight, when you keep on the surface, it exerts force if there's a pressure. But in all such cases, pressure is only one direction. See, looks what happens in case of liquid. That is one thing what we need to really understand well. Pressure in liquid have no sense of direction. It is a scalar quantity, and let's understand why. So if we look at inside liquid, any point, if we take a particular level here, so this is something we'll again in horizontal plane here. At any point, the pressure is same. So how do we understand the direction of pressure? One way to understand direction of pressure, if I keep a thin surface here, this surface will have one side, it will have two surfaces. Any plate, if we keep, it has two surfaces. A small area if I keep, so it is in contact with the liquid on the upper surface, also in contact, lower surface also in contact with the liquid. And liquid exerts contact force in terms of pressure into area. And how would that force act? Perpendicular to surface, and it is always pushing in nature. So here also, which direction of force is acting? Force is acting in this direction. And here the force is acting in the opposite direction. So why this force has become perpendicular? Because here pressure has a particular magnitude, and pressure translates into force only when a surface we consider a surface. And whenever we consider a surface, the pressure gets converted in form of a force perpendicular to that area. So suppose with same level, if we take any other surface also, surface inclined, how would liquid exert contact force in the surface? See, if area is small, over a small area, I can assume pressure to be constant and force will be acting like this. So that's what you need to understand, this how the forces will act at different points. And here also this how, and this external force. So we can find this pressure by checking what force I need to apply on the piston to keep it in a state of equilibrium. So it acts in a direction perpendicular to the surface, whichever surface we consider. And that's how we find pressure inside a liquid. See, we find pressure inside a liquid using laws of motion. And this is something I have gone through last time. So perhaps all of you would recall that part. So if I imagine, basically here, see, to apply laws of motion, I need to first define my system. I have defined the system. Just imagine within this liquid here, either we have imaginary boundary or just imagine this part of the liquid is contained, same liquid contained inside a thin surface. So we have the cellophane surface. Within cellophane surface, this liquid is there. And within the cellophane surface is massless. If we fill up with the same liquid, this liquid also inside the cellophane surface also will remain in equilibrium. If this cellophane is massless and it has no volume. And if it remains in equilibrium, if I consider this equilibrium alone, so contact force exerted by the surrounding liquid can be calculated. So in this case, if we equate force in vertical direction to be 0, horizontal direction, yes, it will, because symmetry, it will cancel out. Vertical direction, forces acting will be like this: pressure at the top surface, pressure at the bottom surface. And since it is in the same horizontal plane, pressure is constant. So I can take pressure into entire area, and the weight. And when we calculate here, we arrive at difference in pressure. This on the pressure is equal to rho g into h. That's the difference in pressure. So compared to this point, the pressure at a lower point is higher by rho g into h, or rate at which pressure changes, dp by dh is equal to rho into g. It is density into acceleration. H is considered to be increasing in the downward direction. So in case of incompressible, unaccelerated liquid, change in pressure between 2 points or difference in pressure is equal to rho g into delta H in the vertical direction. And then we also talked about something like gauge pressure. When we talk about pressure, just take a surface here. And just imagine here. See, if I ask you, if I take this part of the container here, what is the force acting on this part of the container? See, it's not that force is not acting. Horizontal direction, air pressure is exerting in this direction also. Air pressure is exerting force in this direction also. And because forces are equal, they cancel out. It gives an impression as if no force is present here. So, and you just think of it, if you take up something like a water bottle. If you take a plastic bottle, and if plastic bottle inside also is filled with air, and typically unless it is airtight, everywhere outside pressure inside pressure will be same. And you notice even plastic bottle, even if it's not very strong, also it holds its shape. And it gives a feel as if no force is acting. But here also at all points forces are acting, pressure is exerting force, but on the outer surface and inner surface. What will happen if we suck out air from here? Some of you might have done it. With pump or with through mouth, we suck out the air. Suddenly what we find, it crumples. The reason it crumples because the pressure becomes unequal. So in real life, we find effect of pressure, air pressure. It becomes a force only when there's a difference in pressure, when the pressure varies from atmospheric pressure. So what will happen if I increase the pressure here inside the bottle, it will tend to bulge out and it will behave as if there is only pressure exerted from inside. Or if I reduce the pressure, it gives impression as if something is pulling it in. It acts as a suction pressure. That's why the gauge pressure becomes important. So gauge pressure considers air pressure to be zero. Above air pressure is positive, below air pressure is negative. And that's the reason, because net force acting is because of difference in pressure. Net force is due to difference in pressure. And this is a typical example of hydrotic. How do we find out atmospheric pressure? And this is torricelli tube, I think mentioned last time. Very quickly, I'll go through. What is vacuum? Vacuum is pressure is zero. Absolute pressure is zero. No air molecules trapped inside. It will be vacuum. If I keep a tube here, so this point here, this is the boundary between liquid and air. So at this boundary, at this point, pressure will be same as, because there's no depth here. So pressure in air and pressure in mercury at these 2 points will be equal. So this point also will have vacuum pressure, absolute pressure is zero. This point pressure is rho gh. And this pressure, these 2 point pressure have to be equal. So this pressure is rho gh, this pressure is atmospheric. It tells you rho gh is equal to atmospheric pressure. That's how we find out pressure. If we take these 3 points A, B, C, pressure at B and C are equal. And we can atmospheric pressure is equal to 10 to the power 5 Pascal. And let's understand here, atmospheric pressure is like a, see, what does 10 to the power 5 mean? It is 10 to the power 5 Newton per square meter. That's the pressure. And this pressure is equivalent to same pressure would be exerted if we have a mercury in a column of a height of 76 centimeter. And to get same pressure, we need a water column. So if fill up a container, just imagine if air is not there, suppose entire air from atmosphere is removed. So to exert same pressure on any surface which was being exerted by air, if I have a container, earlier, yes, container, even when there was no water here, it used to experience pressure here. This is what is the pressure on a container. Any container, the pressure is equal to atmospheric pressure. And it is there on the both sides. That's why I don't feel the force. But if air pressure is not there, if I had to create same pressure at the bottom of the container, we need to fill up the container to height of about 10 meters. Or if to understand another way, if pressure is 10 to the power 5 Newton per meter square, it means on area of 1 meter square, air is exerting a force of 10 to the power 5 Newton. Or if you think of it, if I have a horizontal area of 1 square meter, and what is the weight, what is the mass I need to keep to create equal pressure, I have to create a mass of 10 to the power 5 Newton. That much weight is necessary to create same pressure as atmospheric pressure. It's a fairly large pressure. Just because it is there on both sides of the surface, we don't feel its effect. Inside the body also same pressure, outside the body also same pressure. Only when we go to That's a definition there. And I did this example. Let's quickly understand that part also. If something is partially evacuated, it means some air has been removed and is airtight container. And if I need a force, so you had seen if the some of them, if there's some kind of suction pressure develop, or we call what has vacuum has developed inside a container, is not vacuum, is partially vacuum. The pressure has dropped below atmospheric pressure. And if it is below atmospheric pressure, we need significant force to pull it open. How do we calculate this force here? We can calculate force by taking the free body diagram of the cap. So one way of calculating, I draw the force, 660 Newton, not into area, and whatever pressure is inside. And if I write the equation, the 60, the upward pulling force has to be greater than P naught minus P into area. And that's what the equation comes to. What is P naught minus P here? This P naught minus P is nothing but gauge pressure. So what is the net force acting? Because when the partial vacuum is created, net force acting because of pressure is deviation of pressure from the atmospheric pressure, which is gauge pressure. So I could have drawn the same figures like this. So this vacuum here gives an effect when it's vacuum. See, when it is more than atmospheric pressure, it will exert net pushing force. And if this pressure is lesser than atmospheric pressure, it will appear, pressure becomes negative. It will appear as if something is pulling it inside. And what is the pressure which is pulling inside? Gauge pressure. So that's the understanding of gauge pressure. And understanding gauge pressure is useful in some of the questions. Coming to typical application of a fluid statics question. And plus these questions are based on two simple things. That's what we try to understand here. Is liquid is shown, it's a YouTube kind of thing, and two liquids are filled. And we know if you fill up the same liquid, both the side liquid will rise to the same level, it will be the same horizontal plane. But here it's a uniform cross section. One side this is water and this is mercury. So one side, if we fill up water, which stands to height of h units here, h maybe this is centimeter. What we'll find if we add liquid water here, which is immiscible, the level of mercury on other side also rise. And if we compare to level of mercury on the left hand side, it has risen by 2 centimeter. So difference in height of mercury column is 2 centimeter. We have to calculate what is the height of water. Now, what we need to understand here, all such question, what an important point here. So we solve such question on very simple pressure. Pressure at 2 points in a communicating liquid at same horizontal level will be equal. So if I take this also liquid here, if I take same horizontal level another point Q here. So if I take in point P and point Q, they are in the same horizontal level, but these are not the same liquid. This level is this is mercury and this is water. So this pressure at P and Q will not be equal. But if I take pressure just inside the mercury level here and same horizontal here, X and Y. Now X and Y, they are in the same horizontal plane. It is same liquid and connected to each other. I can equate pressure at X and Y. So this is an important thing, small point, but we need to pay attention so that unless we go wrong in this. So pressure at 2 points in communicating liquid in same horizontal plane is equal. Or what we can do here, or we can always equate here, we can equate the pressure at the bottom. So to calculate pressure at the bottom here, I can start from here, atmospheric pressure, keep adding increase in pressure from left hand side. I can also calculate pressure from the right hand side. And since it is same point, you can equate the pressure calculated from left limb and right limb. In this case, I will equate pressure here only at this level. If you equate pressure here, and that will add gauge pressure. So what is gauge pressure at X? Gauge pressure will be equal to rho G into H of water. So I'll take rho water. I'm then equating G term I have cancelled. Rho W into H will be equal to rho M into 2 centimeter. Since both sides, if I take H in same units, easily I get my answer. H has to be 2 into 13.6. So this is simple principle. And just look at the next question, which has come in JEE Advanced also, but exactly based on same principle, only thing the figure has changed, and that's what makes it look more complicated. So it is like a circular tube in a vertical plane, and two liquids do not mix each other. They are filled up in the tube so that each of them occupy 1/4 of the volume. So each one of them, if the densities were equal, the left half would have been D1 liquid, and sorry, left quarter would have been D1 liquid, and right quarter would have been D2. D1 and D2, there are densities here. But if densities are not equal, the one which is heavier will tend to go down, which is lighter to tend to go up. Of course, this here, D1 has a greater density than D2. And the boundary, which would have been right here at the vertical, if densities were not equal, it shifts by angle alpha. And very easy to understand, if this moves by angle alpha, this interface also will move by angle alpha, and this interface also will move by angle alpha. What were we required to calculate in this examination? Each liquid subtend 90 degree at the center, radius joining the interface make an angle with the vertical. What is the ratio of D1 and D2? So here also, how do we calculate? I will calculate pressure at this point from left hand side and pressure on this point from the right hand side and equate the pressure. To calculate the pressure depends only, I know the density D1, I need to calculate this height H1 here. I'll just mark what are the things I need to calculate, height H1 here. And similarly, I need to calculate this height H2. And I need to calculate this vertical distance H3. If I calculate these three in terms of angle alpha and radius, I have my answer. That's all we need to do. And let's see how do we write an equation here. So pressure at the bottom of tube calculated from left to right will equate. Okay, so left hand side pressure is density into G into height H1. Height H1 is R minus R sine alpha. So it becomes R1 minus sine alpha. So I have just subtracted this height, which is R sine alpha. Now coming to right hand side, what is this height H1? H1 is equal to R1 minus cos alpha. This is H1 here. And what is H2? H2 is actually this height from here to here we have to calculate H2. So H2 I have taken in two parts. This part is equal to R cos alpha and this part is equal to R sine alpha. So these are terms I write equation and I equate left equation to left hand side to right hand side. I get a ratio of sine alpha by cos alpha. So this also, again, which principle have we used here? Very simple principle, equating the pressure at the lowermost point. Okay, and this also another good question, and this is something just try to understand what the concepts involved here are. In an open tube is immersed in mercury. So this is mercury here. We immerse an open tube in such a way this 8 centimeter extends above the mercury level. So how much the height above mercury level? This is 8 centimeter. And after like this, open and the tube is closed and sealed. After this, we seal it from the top. When we seal it, the top means becomes airtight. So there's some air molecules trapped inside this volume here. And when initially they were at atmospheric pressure. Now, after sealing, this tube has been pulled up. In the mercury, we pull up with some force and raise vertically until the air occupies a length of 32 centimeter. As we keep pulling up, why the length occupied by air is increasing. As we are pulling up, you'll see here that pressure is decreasing. As we keep pulling up, the pressure will decrease, and we have seen in mercury, had this equal to 76 centimeter, the pressure would have been 0, which cannot happen here because there are air molecules inside. So we pull it up such that this length becomes equal to 32 centimeter. Up to what height will the mercury rise here? And this experiment you can do in the home also. You take a glass, any glass you take, and you keep it inverted, like you fill up with some water, and you just try to pull up the glass here. And when you pull up the glass, you can see the water level rising. Let's see how do we solve that question. And this also very simple question. What are the 3 key points here? What are the 3 key points here? Number of moles of air inside the tube remain constant. So once we seal it, if number of moles were n here, even here number of moles will remain same. Okay, and then as the number remains same, as the volume of air increases, the pressure will drop. And we have to assume, unless something is mentioned, it is isothermal process. If it is isothermal process, what would happen here? The pressure P1, V1 will be equal to P2, V2. That's the second thing we can apply to air which is trapped inside. We are treating air as ideal gas. And third thing what we need to apply when we pull it up, yes, air will have pressure P2. And entire area pressure is P2 because with the depth pressure density of air is negligible. So with the depth of pressure is not changing. So whatever pressure air has, the mercury also near the interface will have the same pressure. So liquid near air boundary will have same pressure as surrounding air. Now let's write this equation here. So what is this thing we are going to equate here? First thing I'll find out what is the pressure here. Here the pressure was P naught. So I'm just using P1, V1 is equal to P2, V2. So P naught into area of cross section into 8. We use the same unit, so I don't have to convert here. And that has to be equal to P into A into 32. So this will give me value of P here. So pressure, if the length has become 4 times, the pressure has become 1/4. So pressure inside this part of air is 1/4 of air pressure. And since we are dealing with gas here, we have to use absolute pressure here. The pressure at the liquid boundary, pressure in the mercury also is equal to how much is the pressure? Now what I do here, so this pressure here, so pressure P, mercury also at this level has same pressure P, but mercury at this level will have pressure P plus rho GH, and P plus rho GH here will be equal to P naught. So P naught pressure here minus rho GH is equal to P. Sorry, this is, yeah, this is equal to P. P is equal to P naught 5. So this is the equation we form here. And we can easily understand this has become P naught by, this is 1/4 of the air pressure. So 1/4 of the air pressure, if liquid mercury rises to 76 centimeter when the pressure is P naught, when the pressure is P naught by 4, it will rise to height of 76 by 4. That much height it will rise. That's the answer. Okay. So perhaps these 3 points which is important or relevant here. Yes, Alan?
Sir, initially the pressure inside the tube, sir, won't it be atmospheric pressure?
It is atmospheric pressure. That's what you have taken also.
So then when we raise the tube outside, sir, according to this, the volume of the liquid will
But
decrease.
I think you not paid attention. This top, it is sealed. And that's why I mentioned also. Just go through that part again. See, it has to be sealed here. Is it not? Have we not mentioned here?
Okay, sir, I took even the bottom one as well.
Then bottom one, how would air come from here?
That's what confused me.
No. So air will not come. Okay. So if you are thinking, see, this air will not come from here. Okay. So that's important point. I think some of you also don't think the air will come from here. Otherwise, this previous case manometer also will not work. Okay. Next question. So that's a simple thing on fluid statics. There's something called Pascal law. Pascal law is fairly simple and very easy to understand. And Pascal law is valid only for confined fluid. Confined means, and it has to be airtight. So basically, when we change the pressure, it's not squeeze out. So let's consider and say there's a vessel here, and we have a piston, massless piston, and this airtight. So whenever we talk about Pascal law is it is airtight. So what we consider here, this incompressible liquid in a container, and this piston is massless and frictionless, but it is airtight. And there are several equipments we can see in day-to-day life. Even the car jacks also, it works on the similar principle. So there also is filled up with air. So when it is airtight, what would be the liquid pressure just below the bottom surface of the piston here? See, we can easily find the pressure just below. So if piston is massless, net force on the piston is 0. So it means net gauge on the top gauge pressure is 0, bottom also gauge pressure is 0. So this, if you take in terms of gauge pressure at A also is 0 because it is massless. Had it been massless, it would have been different. Okay, and so if this pressure is equal to gauge pressure, it's 0 here, or I can call absolute pressure is atmospheric pressure. Another point B, which is at a depth, if density is rho, the pressure at B will be equal to P minus PA, it will be higher by PV by PA equals rho GH. So compared to A, the pressure is higher by rho GH at point B. Now what we do, we place some weight here. I placed a block of mass M here, and a block of mass M, liquid is incompressible. Had it been air, the piston would have moved down. But liquid is incompressible, but practically no change in position of piston. But some change will happen in the sense, now on the piston is again in equilibrium. So now if it is in equilibrium, let's see what are the forces which need to act. This weight will exert, this mass will exert a downward force equal to mg. And that extra weight has to be borne by pressure here. So what kind of pressure in terms of gauge pressure? I'm ignoring atmospheric pressure. I'm just make you understand gauge pressure only. So what is pressure here in excess of atmospheric pressure here? Let's see the atmospheric delta P pressure downwards, which is equal to gauge pressure. The pressure here has to increase to support the weight. And how much the pressure will be from equilibrium, from laws of motion, easily arrive at. If mg is downward force, mg has to be equal to delta P into area of the piston, or increase in pressure is equal to mg by s. So pressure at A, if it was gauge pressure terms, it was 0 earlier. Now it has become mg by s. What is the pressure? That's a change in increase in pressure because of extra weight kept here. So whenever you keep an extra weight on a piston-like thing, it becomes pressure increases by weight by area. So area it has increased. How about pressure at B? In between this area also, still the liquid, there's a mass of water, mass of liquid in between. There's a weight in between. There's a gravity in between. So pressure between A and B, pressure difference still remains same. So pressure at B also become delta P plus rho GH. So what happened here? So whatever increase in pressure which was done at point A, same increase in pressure has been transmitted to an arbitrary point B. And other way of saying here, any change in pressure at a point in confined incompressible liquid is transmitted undiminished to all points. So we increase in pressure at one point through some means. Everywhere inside the liquid, pressure increases by same amount. That's the Pascal law. And very simple example of Pascal law is something like hydraulic press. Hydraulic press is something like this, and this is how if you go to any mechanic shop or you go to any automobile service center, it works on a similar principle. This is how most of jacks work, which have hydraulic pressure, and those have to be airtight. And how did this is something what we see here. There are two vessels here, or you can see there's one piston, both are airtight, and two massless piston with load on the top. See, this is small m mass and this is capital M, and they are in equilibrium. If area of the piston, this has area S, and this is n into s, some multiple times s. It could be 100, it could be 50, whatever number, and is greater than 1 here. So if these are the two areas, and if these two pistons are at the same level, what has to be the ratio of mass which piston can support? So what is the ratio of mass? Very easy to arrive at. If I take point A here, if I take point A, gauge pressure at A will be equal to mg by s. That's the gauge pressure we have done in previous case also. And if I take point B also, which is at the same level, gauge pressure will be equal to what? Gauge pressure will be capital mg by s. But these two pressures, since it is same communicating liquid, same horizontal level, pressure have to be equal. So I equate those two pressure. I find whatever ratio of area we have, same ratio of weight. So this is the principle on which a jack works. So if I have, this is something is filled up with some, what you may call as some oil or some fluid here, and we exert weight or we apply force on a small area. If I apply a force F here, if this area is 100 times more, it will support an object which has a weight of 100 F. That's what it does. But only thing what will happen, if I press it down, if I move it by 1 centimeter, this will move by 1 by 100 centimeter volume. So basically what will happen, if I move, whatever work is done by this force, negative work will be done by the other force. Okay, that was the case when they were at the same level. This figure I picked up, this figure somehow not very neatly drawn. This 1.5 meter at the same level. Let's look at this. This figure shows a hydraulic press. In this case, two pistons are not at the same level. So let's understand their method is very simple here, this as well. So they are not in the same level. If one mass is 20 kg, what is the mass it can support? What mass should I place? Because if I place unequal mass, what will happen? The liquid level will start changing. So only with particular when they're balanced, then only liquid remain a liquid level on two sides of, suppose both the side there was no mass placed. What will happen? Liquid will try to come to level, this level will fall, this level will rise if there were no weights were placed on either side of piston. So we have to have certain proportion of mass of weight placed, then only it stays in a state of equilibrium. So which has to be balanced system in equilibrium. So this also fairly simple, pressure at the bottom. So there are two ways whenever the communicating liquid. So okay, this is something, this arrow is right up to here only. Okay, so think the arrow is like this. This is 1.5 meter. So what we'll do here, see this also communicating liquid, it is in the state of equilibrium. So pressure at this point and pressure at this point are equal. So I'll equate the pressure at this point and this point. I take the gauge pressure plus, so what is the pressure on from this side if I calculate, this will be capital mg divided by area is 1 square meter plus mgh, rho gh, sorry, what I'm saying, this rho into g is water into height is 1.5 meter. So this is the pressure on the left hand side. Same level if I take on this side, what is the pressure here? It will be equal to this mass into g divided by area of the piston. Area of the piston is 0.01 meter square. So thus area we get, once we get equation, we can easily find the m value comes equal to 500 kg. So even if they are not equal, still, so if they are at the same level, masses or weights are in the same proportion as the area. But if they are not at the same level, we can just equate the pressure in the same horizontal plane, communicating liquid, and we can form equation, we can solve this question. This also a similar question, just to make sure. So a slightly different format is given. So this also is confined liquid. So here also you can calculate pressure. Pressure will be equal to, so heavy load W supported on platform. Yes, area is S here. So I can easily calculate what is pressure. So what is the force? So suppose there's a piston here. If we do not apply right amount of force, it will be pushed towards right. And if I apply too much of force, it will push towards left. So only when I apply particular value of force, it will remain in equilibrium. And that force has to be equal to pressure into area here. Because there's some pressure here. And we are assuming this area to be small, everywhere pressure to be constant. So this force has to be pressure at this level. And we are assuming this tube to be thin tube here. Something not mentioned, that's the only way it can solve. So if it is thin tube, the pressure here will be same as the pressure here. So let's do the thin tube. So the F is equal to pressure at a depth H into area of this piston. So how do we write? F is equal to P into area of the piston is S by A. If this area is S, this is given S by 10. So F is equal to P into S by A, and P pressure is at this point. And here also, which pressure we take? See, we have really taken only gauge pressure. What happens if I take absolute pressure? In that case, if I take absolute pressure, then I have to add atmospheric pressure here also. That's the reason when one side atmospheric pressure exerts present here, we should better take only gauge pressure. Because I'm not taking atmospheric pressure on this side, and this side also I'm not taking atmosphere. So we always take the gauge pressure. Outside gauge pressure is 0. Inside gauge pressure is positive. Inside the gauge pressure is equal to weight by S here. This weight by area into rho GH. That's equal. That's the pressure. Multiply S by 10 is the force I need to apply to hold it in equilibrium. And this, based on this, Archimedes principle is nothing new, but actually same thing. Application of principle of pressure and force. It says when object is immersed here. So see, even if you don't know our Archimedes principle, anything which is immersed in water, and if it is in the state of equilibrium and liquid also not in motion. So whether liquid is, in this case, whether the liquid is viscous or non-viscous, if they are at rest, doesn't matter. If it is at rest, the force will be always normal to the surface. So how would the force act if I display? If I take all small areas, this is how the forces on a small areas will act. And what you notice here, I have shown the arrow here on the top, arrow length is smaller, because here the pressure will be lower here. And here it is at a greater depth, pressure become higher. So same area, if I take here, and if I take same area here, the pressure force, this upward force will be greater. So this how forces will act, and very easily we can notice if I take corresponding areas and we take calculate force on the corresponding areas on either side of the sphere, they will tend to cancel out. So all horizontal components cancel out. Net contact force exerted by the surrounding liquid on this sphere will be in the vertical direction. That's called force of buoyancy. So any object is submerged in liquid at rest, contact forces with the liquid will be normal to the surface, and resultant of all forces, if I add it up on a small area, and for any defined shape, actually it is mathematically also very easily can add it up. It is sphere, we can do that. We can add up resultant of all forces. We can take that ring kind of thing. We can take a ring which is at a common depth. And we can calculate net force is equal to weight of the liquid displaced. That is Archimedes principle, and it can easily be proven. And this is case, there are two cases. One is fully submerged, and other cases I have taken a regular shape. If it is a regular shape, it is a cuboid kind of thing. In this case, it's even easier to understand. It is partially submerged. So it's submerged up to a depth of h. And this has a surface area s here. Now, in this case, without Archimedes principle also, I would have known what is the net force. I'm again here on the top also atmospheric pressure is acting, and bottom is atmospheric pressure plus this. So everywhere where atmospheric pressure is present, I'm cancelling atmospheric pressure. I'm only calculating gauge pressure. So I'm taking this pressure is 0. The pressure at the bottom is rho gh. So at this level, pressure is rho gh, and this surface is horizontal. Force will act due to pressure on the perpendicular direction or vertical. So force acting on the this cuboid. Contact force exerted by the surrounding liquid it is in contact with. Resultant of that will be vertical, horizontal will cancel out, and that force is equal to this. But when this force, we write something like this, what is H into S is equal to? See, H into cross-section area is nothing but this volume. And that volume is nothing but volume of liquid displaced. So when I say this is volume, this density becomes mass and this becomes G. So what is this net contact force exerted by the liquid, which is on a submerged object, partially submerged object, is equal to weight of the liquid displaced. So contact force on the boundary by the surrounding liquid. So that's third way you can understand. And if you understand this, I think this is more important than any other fashion. Assume that this is something, and this is a sphere. And this sphere again is like a thin, it's a thin cellophane sphere. And thin cellophane sphere, inside this I filled up with the same liquid. If I drop the liquid spherical, if I drop this sphere and the liquid here, this would have remained in rest because it's the same liquid. It would have remained in rest. And would have remained in rest, why it is not sinking down? Because this liquid which is contained inside the boundary of cellophane, it contact force exerted by the surrounding liquid. And we can very easily understand if it is same liquid will remain in equilibrium. So net contact force is equal to weight of the same liquid which is contained within this volume. So one way to understand this is something is so contact force by the boundary by the surrounding liquid is same regardless of what does the boundary contain. Now within the cellophane it was liquid, it will remain in equilibrium. If I fill up within the cellophane some other liquid, will the contact force by the surrounding liquid change? Surrounding liquid has not changed, surface has not changed. So contact force is independent of what is contained inside the boundary. So whether it's a copper ball, is a iron ball, or it is a something cellophane of this spherical shape containing liquid, all cases force remains same. The contact force doesn't depend on the nature of the boundary. It depends on the shape of boundary, volume it encloses, not what is contained inside. Object be partially submerged, that's also we understand. When body is fully submerged, fully or partially, both cases it is same, and it's unaccelerated liquid. Then liquid exerts a net upward force equal to weight of the liquid displaced. That's a simple Archimedes principle. And the same thing we could have arrived at even whenever the shapes are regular. We can arrive at, we don't need to apply, even with laws of motion also, we can arrive at the thing. Now let's look at some questions based on Archimedes principle, submergence and all. So there's what we notice here, there's a spring which is supported from here. And it is in normal length here. So when I support a mass m here, it gets elongated by 5 centimeters. So any solid object when suspended by a spring produces an extension of 5 centimeters, and then it is fully immersed in water. So bring a water vessel here. When it fully immersed in water, what you find, this extension in equilibrium becomes less. Now it has extended only to 3 centimeters. So let's understand if that has happened, what is the specific gravity of this material? What is the specific gravity of the solid? So let's look at very simple first case equilibrium. And whenever we deal with questions related to force of buoyancy, we'll use the volume of object which is getting submerged. So here also this mass or its weight will write in terms of volume. So mg is equal to density of the material, density of the solid into V into G is equal to kx. It is in equilibrium. So k into x by 100. That's the first state. And in second case, what has happened? Second case, when it is submerged, and you can see if you have any steel ball, just try to hold the steel ball in your hand. Some of you have dumbbells, metal dumbbells at home. Just hold the dumbbell in your hand and then just submerge the dumbbell in the bucket of water. Immediately you will feel as if the weight has reduced. Thus, in that case, what happened? Moment you submerge, earlier you had to apply an upward force equal to weight of the object. But moment you submerge inside liquid or water, force of buoyancy starts acting. So to the extent the force of buoyancy start acting, the apparent weight gets reduced. So what is apparent weight of an object which is submerged in a liquid is FB minus MB. Mg minus force of buoyancy, and that becomes equal to apparent weight is K into extension. Now we write simple terms. So what is FB equal to? FB is equal to rho W Vg. If you write rho W Vg, it becomes rho in more general rho liquid. This expression I get here. Once I have this expression, I take the ratio, I get the relative density. So once we understand how to form equation, we can easily get this answer. You can do that. So I'll move on to some more question. And one more important, an object of copper. And actually, this is the kind of thing which has, this is similar kind of observation which has led to Archimedes' principle. He observed something similar. An object of copper having cavity. So it is not cavity, weighs 264 grams in air and 220 grams in water. So whenever you take gram, it's basically, this always weight is attached here. Okay, so we measure mass and we understand it's always implied. Okay, so that's when we say gram, actually is gram weight. But it's very common, so we understand what it should be. So this game in air and this in water, and density of copper is 8.8 grams per cc. Find the volume of internal cavity. So this can happen in any object. What is the cavity it has? So what we notice here, when we submerge in water, apparent weight is reduced. But what is the reduction here? So apparent loss of weight is due to weight of liquid displaced. And weight of liquid displaced is equal to density of liquid into volume submerged into G. So loss of weight in grams in water. So when we calculate for water, in case of water, this density is 1 gram plus cc. And if I take this also, the volume also in terms of cc, so this one here is what we obtain here. So loss of weight of gram. See, basically because 1 gram is equivalent to 1 cc, here loss of weight is equal to 43 gram. It is 43 gram because it has displaced 43 cc of water. So loss of weight in gram in water is equal to volume of object in cc. It's a very simple thing, and this is something we should keep in mind. So here indirectly, moment I find what is the reduction in weight, indirectly I find volume of the object. So gross volume, which is total volume submerged, is equal to 43. So that's a very apparent loss in weight is equal to its gross volume. Once we have gross volume, I can also calculate, since I have its total weight here, this weight is composed of only the copper. And since we know the density of copper, we can calculate what is the actual volume of copper present in this object. Actual volume of copper present in the copper is equal to solid volume is equal to total mass by density, which comes to 30 cc. But when I submerged here, I found the gross volume is 43. So what does this imply? It means this cavity volume is 13 cc. Okay, let's look at one more question. There's something, if you take something like this, you can it could be water or some other liquid. So we have two spherical objects. One object has a density of half the density of the liquid. Other object has a density of 2 rho. Both are immersed in liquid of density rho, and they are held in the middle of the tank. So suppose you actually do this one. If you have water, so one, you can have an object which is something like, you can have much heavier than water. You can have a metal ball, and you can have something like some plastic ball, which is half the density. And you know, if it is something, if you hold it like this, on this to keep it in rest, you need to apply force in the upward direction. And this will tend to come, you have to apply force in the downward direction to hold it in a state of rest. Now, question is, what will be initial acceleration soon after release? As soon as you release, what will the acceleration? And before that, if both are of the same radius, force of buoyancy on two balls are identical because contact force nature acting will be same. So both will have same force of buoyancy. And that force of buoyancy, if we have a third ball, which is same density of the liquid, this ball would have experienced, this also would have felt same force. Contact force does not depend on what the surface encloses. Contact force is same, force of buoyancy is same on both of them. And what is the acceleration soon after we release it? Acceleration is equal to net force. Net force will equal to weight minus force of buoyancy. I'm taking mod. If I take what is the acceleration divided by mass. So what would be the magnitude of acceleration? If I write weight into weight, how do you write weight? Density of the solid into volume into G. So this will become rho s minus rho L, force of buoyancy, divided by rho s. That's acceleration. And depending on which one is more, in case this density is more, so what would be acceleration of this solid object? If I substitute it here, for object A, I would have written, this would have become rho by 2 minus rho divided by rho by 2. That's the acceleration of A, which comes equal to G. Which direction? Upward direction. And how about acceleration of other object? I will calculate here acceleration of solid. This is 2 rho minus rho divided by 2 rho. It will become G by 2. So as soon as you release, it will have upward acceleration of G, and this will have a downward acceleration of G by 2. So there are quite a few questions which can be formed. See, all laws of motion can be converted into a fluid mechanics question. So all fluid mechanics question, one additional force which comes into picture is contact force exerted by the fluid, which mostly can take as force of buoyancy. So they are all laws of motion question can have a similar question framed in case of laws of fluid mechanics also. Many questions of fluid mechanics are floating. Floating is nothing but equilibrium. Any object is floating, it means in a state of equilibrium, net forces have to be zero. So moment I see floating, I understand this equilibrium question. There's one additional force, force of buoyancy acting, the rest all is laws of motion. So hollow metal ball of outer radius r is just floating. So whenever we cross just floating, it means complete volume is submerged. So in this case, whenever it has just floating, so volume of the object is equal to volume submerged. That's what it implies. Full volume is submerged. The specific gravity of the material is 8 by 7. If specific gravity is 8 by 7, it means its density is 8 by 7 into 1000. So if this is given, our radius of ball is r, what we need to find? We need to find what is the radius of cavity. So that it is floating. So very simple, on whenever it's a floating question, we equate these two. Weight is equal to mass force of buoyancy, and the volume of cavity be V dash. Whenever we take a force of buoyancy, we need volumes here. Let the volume of cavity be V dash here. And this volume is known anyway. So what is the weight equal to? Weight is only because of weight of metal. So weight will be equal to density of the metal. This is density of the metal into volume of the metal into G. Volume of metal V minus V dash. And that will be equal to rho W, same V. Because volume submerged, I should have taken this as this. What is V here? This is volume submerged or volume displaced. Volume displaced, since entire ball is floating, this we can write V. And from here we can easily find V dash, which comes equal to V dash we can find, and we can find the radius also. This question, all of you should try and do on your own. They're fairly simple questions. Another one more question on ornament agreement, and this is based on what Archimedes discovered his principle. Because the king gave him the task, he had some ornament. He felt that ornament is not made of pure gold. It has been mixed with copper. He told him to find out, tell me what is the proportion of copper mixed in gold. And when it's mixed together, it has, basically when you heat it and melt it and to make it together, it becomes difficult unless you remelt it and then separate. Instead, you find out how much is the how much proportion of copper is mixed in the gold without disturbing that ornament, without damaging it. So it's something like this. So that's what he can do. This is how we can find out what is the proportion of copper which is mixed, and we can find out because the density of gold and copper are quite different from each other. Let's see. So what I did, ornament, you take the weight in air, it comes to 36 grams. You submerge in water, you find the weight has come 34 grams. So what is the difference between the two? What does 2 gram indicate? 2 gram indicate 2 cc is the gross volume of the ornament. Whenever we say density of ornament, so 2 cc is the mass of the ornament. If 2 cc is the volume of the ornament, it means that the density of the mixture is 18 grams, 36 by 2. If this means 36 gram and volume is 2 cc, if this density, I can calculate what is the proportion of mass by using, okay, so let the mass of copper be m, and hence the mass of gold is 36 minus m. So I add these two, I calculate the gross volume of these two. These two volumes should add up to 2 cc. That's how I find the equation. So what is the equation we found? Total mass by total volume has to be equal to 18. Volume is by divided by respective density. M divided by 8.9. M is the mass of copper, and remaining mass divided by density of gold. And by solving, you get M is equal to 2.2. So this is something, this is what Archimedes principle he used to find out how much copper was mixed in the ornament. What proportion? Okay, this is also another similar question. This is something you would notice here. If a tank is deep enough, even in the aquarium also you can notice sometimes the bubble forms, bubble contains air. And if you pay attention, and if the tank is deep enough, what you notice as it keeps rising, the size of bubble keeps increasing. So it has certain size at the bottom. When it comes to the top, size has changed. So volume of air bubble becomes 3 times as it rises from bottom to the lake to the top. So if this volume is V here, it has become 3V here. Okay. So this what given, what is the approximate depth of the lake? And we are talking, when I take, we are talking water here. Lake is, we are assuming, which is water. So in this case, pretty simple. So why has the volume increased here? Because there's air trapped inside. As the pressure reduces, this all such cases, what is implied here, the temperature is constant. P1 V1 is equal to P2 V2. And since we are using ideal gas, we cannot use gauge pressure. We need to use absolute pressure. So pressure at the bottom is thrice the pressure at the surface here. Pressure at the surface is atmospheric. It means pressure at the bottom has to be equal to 3 times atmospheric, or increase in the pressure is equal to 2P naught. So increase in pressure due to height h of water column is equal to twice the atmospheric pressure. So what has to be h here? I can write that equation, or I know atmospheric pressure, 1 atmospheric pressure is equal to 10 meters of water column. So twice atmospheric pressure will be equal to 20 meters of water column. So this height has to be equal to 20 meter. Or I could have written this equation also. Yes?
Sir?
Yes?
Sir, when we use this P1 V1 equals to P2 V2, isn't it supposed to be the pressure like inside the air bubble, or is it the pressure acting on the air
all
bubble?
such cases, there's one more thing which is implied. It has to be pressure inside the air bubble. See, and what is implied here? This is, yes, of course, we are taking pressure inside the air bubble, and pressure inside the air bubble. We are also, I think maybe I should have written one more thing is implied. Pressure inside the air bubble, we are assuming it to be same as the pressure of the liquid just outside. So there's no, this pressure is equal to pressure of the surrounding liquid. So we are not taking excess pressure. Whenever question is given and surface tension is not given. So what we assume, see, when we calculate net pressure is composed of two things, outside pressure plus excess pressure inside the bubble. And since we are taking absolute pressure, if this is much, much higher than this delta P, we can ignore this delta P. So excess pressure because of surface tension inside the bubble. Normally this much smaller. Here we are talking very large value of pressure. So compared to this is negligible. And you can easily understand also, you understand how large these atmospheric pressures are. This is 10 to the power 5 Newton per meter square. And these are much, much smaller. They are order of few Newton per meter square. That's why it can be neglected. Okay. Okay, next one is something like this, also very common question. It has come in, it may come in different forms. So we need to understand what is the underlying principle here. So there's a wooden block. So if we know wooden block has a lesser density than density of the water. So we have wooden block, it will float. So it is floating and it has some depth of submergence. And on the top of wooden block, I can keep a coin, or you can keep up something like this, something metal object, a piece of iron. So when we piece a piece of iron, what would happen? Unless it is too heavy, it will sink further. The wooden block would sink further. So what is given here? A wooden block and coin is placed at the top, floats in water as shown in the figure. And this experiment also one can easily do at home. You can take a wooden block, take a piece of metal. It could be piece of iron also. And we see this is something, if it is a glass vessel, you can see from outside. And when it is in equilibrium, this is the depth H and this is the depth of the water. And whatever depth of water we observe, if a wooden block was not there, earlier the depth would have been lower. So when we put the wooden block, when we insert the wooden block here, the depth of the liquid changes. So let's understand what are the few points here. First thing what we understand here, when we see this depth of water, this depth of water is depends on what? It depends on, it reflects volume of the liquid and the volume displaced. So this level of water, if I take cross-section area of the tank here, multiply by H, that will be equal to volume of water plus volume of water displaced. So liquid level corresponds to not only volume of liquid, it also includes volume displaced. So when coin is on the block, the volume of liquid displaced, what will volume of displaced be equal to when the coin is placed here? This is the volume which is displaced. And this volume displaced will be corresponding to weight of the coin plus weight of the wooden block. Now, so when we place this coin on the top of wooden block, what is the extra volume will get displaced due to placement of coin? When we place this coin, extra volume which gets the density of water into G has to be equal to mass of the coin into G. So that's the extra volume. So the extra volume which is getting displaced is corresponding, that's what is extra volume displaced. The basic density of the coin into volume of the coin divided by the density of the liquid. So, but when the coin falls, so this is the volume it is displacing when it is floating. When the coin falls, the coin goes inside. So first, as it start falling, just assume I have removed the coin first. If I remove the coin, it will go up. It will go up by what volume? The whole block will go up by which volume? It will go up by this volume. But as the coin falls into this, again, it will displace volume equal to its own volume. Now, after it falls, the volume of liquid displaced is equal to its own volume, and its own volume is Vc. And you can easily notice here, since rho c is greater than rho l, earlier Vd is greater than Vc. So when it is floating, it is displacing volume Vd. When it does submerge, it displaces volume Vc. So volume displaced becomes smaller. If volume displaced becomes smaller, what will happen? The level of water in the tank also will go down, and block will rise. So these are the points you need to keep in mind. This is something, this kind of question, that's what you need to understand. When it is floating, just the volume displaced, and thus the water level also be higher. And as if I remove the coin, water level will rise, and so water level will rise. But as soon as I drop the coin, again water level will fall a little bit, but rise in level would be equal to Vd. And again sorry, what I'm saying. When I remove the coin, water level will fall. By what level it will fall? It will fall corresponding to Vd. But as we dump the coin inside the water tank, it will rise by volume equal to Vc. Vc is lesser than Vd, overall water level will fall. So we can easily answer this question. So what will, after some time the coin finds in the water? Of course, L will decrease because lesser weight now. And what will happen to height here? Will the total volume is more, water will become less, hence H also will decrease. Both L and H will decrease. But rather than understanding question, I think these points you need to understand. See that these points are clear. All right. So I'll stop here now.